Understanding forces is one of the biggest essential understandings in a introductory physics mechanics class. A force is a push or a pull that one object exerts on another. There's kind of two broad categories of forces: contact forces, which are kind of like a generic, I pushed something, or, the object is sitting on the table. I'm pulling something with a rope. There's a friction force. All of those forces involve contact. The two objects must be touching each other in order for those forces to act. There are other forces called field forces that don't require contact. The most common one that we use is gravitational force, right? The Earth's gravitational field allows the Earth to pull down on you, even though, you might be jumping in the air, not actually in contact with the Earth. Thankfully, the Earth is still pulling you down towards its center. So gravitational force, electric force, magnetic force, all of these have associated fields with them. They do not require contact, but for the most part, the forces that we work with do, which is something that we will find useful when we are drawing free body diagrams. This is kind of like the draw the picture step in setting up the problem. It's going to show all of the forces that are acting on the object. And a force is a vector, so we represent vectors generally with arrows. When we are drawing our forces, the size of the force is given by the size of the arrow. The direction of the force is given by the direction of the arrow. So here, if we just have a cardboard box sitting on the ground, the Earth pulls it down. That's Fg, the Earth on the box. And then the ground, right, is supporting the box. It's preventing it from, falling through to the center of the Earth. We would call that a normal force from the ground on the box. When we draw our forces, the starting point, like for the tail of the force, is going to be important. Not so much now, but later on. Generally, gravity is going to act at the center of mass of the object, and contact forces are going to be drawn at their point of contact. So that's why the normal force is touching the ground on that picture. Let's say we are going to pull this box with a rope. Okay, so then there would be a tension force, and so this tension would be the person pulling on the box. And then we'll also throw in a friction force. This is going to be friction from the ground, the rough surface, also acting on the box, opposite of the velocity. A lot of times people get really excited, and they also include velocity and acceleration on the free body diagram. Don't do that. Velocity and acceleration, while they are vectors, they are not pushes or pulls. Changes in velocity, acceleration is caused by forces, but they are not forces themselves. They are the result of a force being applied. Okay, so you can indicate them nearby, but do not draw them on your free body diagram. Okay, so this brings us now to Newton's first law. Everyone's heard of Newton's 3 laws of motion. And so we'll start with the first one, which I think in formal language says, an object in motion will stay in motion, and an object at rest will stay at rest until an unbalanced force is applied. All right, something along those lines. In plain speak, or in kind of intro physics speech, the part that says an object will continue its motion, that means there cannot be any changes in its motion. It cannot accelerate. It must continue with the same velocity. Now, whether that velocity is 5 meters per second or 0 meters per second really is going to depend on the situation. But as long as it's not accelerating, that must mean that there are no unbalanced forces, or in a kind of roundabout way, that must mean that the forces are balanced. Okay, we would say that the net force, or like the total force, on the object is equal to 0. So that kind of sideways M, backwards 3 thing, it's the Greek letter sigma. It means the summation. You may have seen it in your math class. It means you have to add up all of the forces that are acting on the object. And if you do that and it's equal to 0, then your object is in equilibrium. Okay, which means balance. You've probably heard this in your chemistry class before. Well, like when your chemical reaction equations are balanced, sort of the same thing here, except specifically in the context of forces. Our forces are balanced, the total force, adding up all the left, right, up, down. It's all going to cancel out. One of the things that people sometimes overlook, just because an object is traveling to the right, doesn't mean that there is a net force on it. Okay? If it is traveling with a constant velocity, that's the key phrase, then the forces must be balanced. So, for example, here, I have started the free body diagram for a car moving at constant velocity. Obviously, the weight is pulling down. Obviously, the normal force from the road, right, is supporting the car, preventing it from falling through the road. No sinkholes here. When you are driving at a constant velocity, your engine isn't off, right? It's like you've got cruise control on. So there is a forward force on the car. And it's actually from the road, right? Thinking about, well, this is probably going to be a contact force. What does the car need to be in contact with in order to go? Well, it needs to be in contact with the road, right? It's where the tires, the rubber meets the road. So with these three forces, my up force is balanced by my down force, but this rightward force from the road pushing on the car forward isn't balanced by anything. So if you think about it, well, if I'm going at cruise control, it's kind of noisy in the cabin because of air resistance. So that's going to be the force that balances out the force that is applied by the road, by the engine, essentially. So a neat thing about this, once you get to this point, you get to write a net force equation. So that's where you start. Sigma F is equal to, well, in this case, it's 0. Oh, so I've written an equation for the x direction, and I can also write an equation for the y direction. So just like with projectiles, we do have to split up our horizontal components and our vertical components. What happens in the horizontal direction doesn't affect the vertical and vice versa. A lot of times in one of the directions, the forces are balanced, so you don't always have to worry about both directions. Here, everything we're talking about today, everything is balanced. But there is also a neat graphical trick that you can do. So I've literally just copied and pasted my little arrows from up above. So FG is going down, F road is going right, Fn, the normal force from the road, is going up, and then air resistance is going to the left. And if you notice, I have ended back where I started. If this were a displacement vector diagram, this would mean that my displacement is 0. But this is a force vector diagram, so that means my net force is equal to 0, which is nice. Okay, that's kind of a graphical way of proving it. So I've got another sample problem here. Let's say that we are rescuing a gazelle from falling into a pit with cacti at the bottom. So this is kind of weird because the gazelle is at an angle, right? But gravity is always going to pull straight down. So that's a little, okay, that's fine. But then the normal force, so the normal force is from a surface. It's actually like an electrostatic repulsion. It's like electron-electron repulsion that maintains an object's integrity. Anyway, the word normal in this context, it doesn't mean like the opposite of weird. It means the math definition of normal, which is perpendicular. It's like how the word tangent means parallel, right? You have a normal line and you have a tangent line. They're kind of like, I don't know, siblings that don't really get along. They're opposites. So when we're talking about a normal force, we are talking about a force that is perpendicular to the surface. So here I've drawn the normal force perpendicular to the surface of the incline. Ooh, that's weird. It's at an angle. Jumping ahead. We also have this person, right, pulling on the gazelle. He's got a vine wrapped around it, the gazelle holding it in his teeth. He's getting pulled up at a constant velocity. So there's that tension force going up the ramp, kind of parallel to the surface of the ramp. So I'm not going to do any fancy math right now, but I'm going to show you that cool vector addition thing. Check it out. I'm just going to copy and paste my forces from before, and look at that. Right, my net force is equal to 0 because when I add these vectors tip to tail, okay, treating it like kind of a pirate treasure map, okay, I ended up at my starting point, or in this case, my net force is equal to 0. Okay, there is no resultant force here. So that's kind of neat. I just have one last thing to talk about, and that's the difference between mass and weight. I know in everyday English we kind of use these two terms interchangeably. In physics, though, they do have specific definitions. Okay, mass specifically refers to the amount of matter, okay, that is in an object. Mass is also synonymous with the word inertia, which we all know from Bill Nye the Science Guy. It is a property of matter. But specifically, it's the property of matter that governs an object's resistance to changes in its motion. It's how hard is this object to accelerate? Is it hard to start? Is it hard to stop? Is it hard to turn? Okay, so objects with a lot of mass have a lot of inertia. They're very resistant to changes in their motion. Okay, weight, on the other hand, it's gravity specific, gravitational field specific. Okay, your weight is going to change if you are, an interplanetary explorer going to visit other planets in the solar system. Your weight, okay, the attractive force that is due to a gravitational field, your weight is going to change. And there's a specific formula for weight, okay, which is equal to the mass in kilograms times the gravitational field. So I know in physics, our standard unit for mass is the kilogram. I know in chemistry it's the gram, whatever. We use kilograms, right? And then this lowercase g that's getting multiplied by the mass in kilograms. Wait, this is the gravitational field, but haven't we used this letter before? Yeah, and it is exactly what you are thinking. This is the gravitational acceleration that this object is going to experience in this particular gravitational field. So hold on. Let's think about units here, because if mass is measured in kilograms, weight can't also be measured in kilograms. So a kilogram times a meter per second squared. We kind of have this compound unit here represented by a capital letter N. This is called a Newton. Okay, and this is the standard unit for force. It is a kilogram times a meter per second squared. Sometimes, instead of gravitational acceleration, little g, written in units of meters per second squared, you might see it as newtons per kilogram, and you can see it's just a little bit of a rearrangement of the units over there. All right, you get meters per second squared by itself. You can see it's equivalent to a newton per kilogram. So don't be freaked out if you see newtons per kilogram for little g. All right, so the very last thing that you might encounter is you might be asked to design an experiment that uses a method to determine the gravitational mass. And you have to determine, you have to come up with this method. You have to write the experiment. If you are asked to do this, we are trying to set the gravitational force equal to some known force. So frequently you'll see it in terms of a spring scale, right? A spring, in a grocery store, has markings on it. It's already calibrated to the weight of an object. It's already calibrated to Earth's gravitational field. But that is how you'd go about determining the gravitational mass. Okay? Your gravitational mass should be the same as something called inertial mass. You might be asked to come up with a method for determining the inertial mass. Here, it's a little weird. Your method should be able to work even in the absence of gravity. Really, you are looking at this object and you are seeing how it responds to a force of a known magnitude, right? A really, really heavy object won't accelerate very much, whereas a light object would accelerate a lot. So you're observing this acceleration and you're able to make a mathematical statement, about what that mass is in relation to the known applied force and the observed acceleration. But that is a topic for another day.